In this lesson, we're going to learn how to use the VSEPR theory in order to predict the three-dimensional shape of molecules and polyatomic ions. VSEPR stands for valence shell electron pair repulsion. And this theory is based on the fact that electrons around a central atom will repel one another, and therefore we want to arrange them in a position so that they will minimize the repulsions between the electron pair domains. In this theory, single bonds, double bonds, triple bonds, and lone pairs are all equal to one electron pair domain. So electron pair domain is like an area of space where electron pairs can be found. Now, each of these will require a different amount of space, which we'll discuss as we go through. When looking at this theory, we're going to encounter electronic and molecular geometries of molecules and ions. The electronic geometries will result from the arrangement of the electron pair domains as far away from one another as possible around the central atom. And it's determined by counting the total number of electron pair domains of the central atom in the Lewis structure. The molecular geometry shows the arrangement of the atoms around the central atom, and we focus on the resulting shape of the molecule. Although it takes into account the space that's required by the lone pairs, when we're looking at the shape, we are really just looking at how the atoms are arranged. Now, for this reason, when there are no lone pairs, the molecular geometry and the electronic geometry will be the same, as you'll see in our examples. And what we're going to do is move systematically through all the possibilities of the molecules so that we can see all the possible shapes. The system that we're going to use to classify the molecules is using A, B, and E. A will represent the central atom of our molecule or ion. B will represent the atoms attached. And when we have an E, that will represent the lone pairs that are attached to the central atom. So we're always going to start with our Lewis structure. So in this case, if you have drawn a Lewis structure that has one central atom and two atoms attached, you will have all the electrons organized around that central atom. So in this case, you might have something like this that has two double bonds. Now, the first thing that we do is we look at the central atom and we count the total number of electron pair domains around the central atom. In this case, we've got two bonding electron pair domains and no lone pairs. Now, you'll note that even though I drew a double bond in this Lewis structure, I still counted this as one electron pair domain, keeping in mind that electron pair domain is an area where there are electron pairs. Now, in this case, we want for the electron pairs to be as far away from one another as possible. And the angle that we need in order to achieve that is one that is linear. And we have 180 degrees between the electron pairs. So the geometry is linear. The electrons are arranged in that way. Now, in this case, because I have no lone pairs, the molecular and the electronic geometry are going to be the same. So if I want to draw the 3D picture, I need to consider all of the electrons around the central atom. So the double bonds will still appear in the 3D. In my 3D picture, I don't need to worry about the outer electrons on my attached atoms. Okay, and the angle here is 180 degrees. Our next class is AB3. So we would have a Lewis structure where we've got a central atom and we've got three other atoms attached. Now, this is an appropriate time to note that a Lewis structure is really only a two-dimensional picture, and the point of a Lewis structure is to help us to determine the location of the electrons in the molecule. But there's no reason why you should feel the need to, while you're drawing your Lewis structure, to try to predict the 3D molecule. Okay, we can't predict the 3D molecule until we know exactly how the electrons are arranged. and that includes any lone pairs that might be on the central atom. So in this class, AB3, we have 3 electron pair domains total. In this molecule, all of them are atoms bonded to the central atom, and we have no lone pairs. Now what we want is to have a molecule that's going to achieve the greatest angle between the electron pair domains. As it's drawn right now, the angle here is 90 degrees, the angle here is 90 degrees, and the angle here is 180. If we organize the electrons in a trigonal planar geometry, that's going to give us a more ideal angle, and that angle will be 120 degrees. So this angle is 120 degrees. And we call this geometry trigonal planar because this will be a flat molecule. It would be able to lie on the desk. And it's trigonal. It forms a triangle. So that's where the name comes from. Like in our first example, we have no lone pairs, so our electronic geometry and molecular geometry match each other, both trigonal planar. So this is the 3D picture. In our next class, we have AB2E. So in this class, we have 2 atoms attached to the central atom, and we have 1 lone pair. So we have a total of 3 electron pair domains, as we did with the AB3 class, but this time 2 of them are bonding and 1 of them is non-bonding. So you'll see that the electronic geometry and molecular geometry will be different this time. Because there are a total of 3 electron pair domains, we still have a trigonal planar arrangement of the electrons. But this time, we're replacing one of the bonds with a lone pair. So what we are left with is a molecule that is of a bent geometry. Okay, so although the electrons are arranged in a trigonal planar geometry, the actual molecule itself is considered bent, and that's its molecular geometry. Now the angle here, because a lone pair actually takes up a bit more space than a bonding pair of electrons, the angle here will be a little bit less than 120 degrees. Our next class of molecules is AB4. So this is a case where we have a central atom A with 4 atoms attached. Now in this case, we're no longer going to have a planar molecule. If we left this planar, we would have angles of 90 degrees, and we would not be taking advantage of the space above and below the molecule in order to reduce the angles and therefore reduce the repulsions of the electron pairs. So therefore, we have what is called a tetrahedral geometry. In this geometry, we'll achieve bond angles of 109.5 degrees, and that is much more ideal. Now, a tetrahedral geometry will have some 3-dimensional structure to it, so we need to use some known diagram skills in order to represent this molecule. Chemists use wedges in order to represent bonds that are coming towards us, and they use dash wedges in order to represent something that is going away from you. So what you need to be able to do is train your brain to be able to see that this is coming out at you and this is going away from you. Okay? And the atoms are attached. And all of the angles here, the angle BAB, they're all equal to one another, and they are all 109.5 degrees, which, as you can see, is better than if we left it with this geometry, where the angles are all 90 degrees. And what I'll do is I'll use a different color here to show you the tetrahedral geometry so that you can see how this is actually a tetrahedron, okay, which is a shape that has 4 sides that are all triangles. Okay, and this is quite a symmetrical molecule. If you flipped it around, it would look the same all the way around. Okay, so you want to work on being able to visualize that from the diagram. In our next class, we have AB3E. So that means that we have 3 atoms attached and 1 lone pair. So because the total number of electron pairs around the central atom is 4, the electronic geometry is going to be tetrahedral. So we have that same basic geometry. So it's important that you are able to just quickly represent the tetrahedral geometry. So what we're going to do here is we're going to place 4 electron pairs, 3 of which will be the B, and then 1 is going to be a lone pair. Because the angles are all the same, it really doesn't matter where you put the lone pair in this particular diagram. I like to put it on the top so that I can see the trigonal pyramidal geometry that results. So this is a little pyramid. A way to avoid memorizing all the geometries is to be able to visualize them as much as possible. Okay? And if you know your basics, like the tetrahedral, then you can build the trigonal pyramidal quite easily from that. So this is the 3D picture. The angles here will be a little bit less than 109.5 degrees. Our next geometry is AB2E2. So that means we've got 2 atoms attached to the central atom, and we've got 2 lone pairs. This is like a water molecule. Because there's a total of 4 electron pair domains, the arrangement of the electrons, or the electronic geometry, is going to be tetrahedral. So again, tetrahedral is this geometry. So what we're going to do is we're going to replace 2 of these bonds with lone pairs, and we'll be left with, if we want to keep with the basic structure here, we'll be left with a bent molecule. Now this diagram is just showing you the effect of the lone pairs on the bond angle. CH4 is an example of a tetrahedral molecule that's perfectly symmetrical, with the angles being 109.5 degrees. The lone pair in NH3 will reduce the angle, the HNH angle, but as you can see, it's not that drastic. It is a measurable difference, but it is not that large. And the lone pair requires more space. It repels the other electron pair domains a little bit more, so therefore the angle is a bit smaller. And then in water, when we've got 2 lone pairs, the angle is even smaller. Now you'll see in their tetrahedral diagrams, they've drawn them flipped around, but it's the same. You can draw the wedge and the dashed line on the right or on the left. They just need to be on the same side of the molecule. Our next class of molecules is AB5. So in AB5, we have got an expanded octet where we have 5 atoms attached to the central atom. Now, in order for this to be best spread out, what we are going to have is actually 2 planes. We are going to have an equatorial plane, which is even with the equator, so it would be flat on the table in front of you. And then we have an axial plane, which is coming up above the table and below the table, okay, which is perpendicular to the equatorial plane or the equator. So if you hold this molecule in front of you, what you'll have is 3 atoms in a T shape. And then what you're going to have is 1 coming towards you and 1 going away from you. Now you'll see that there's a difference in the angle of the wedge and the dashed line. These are in the equatorial plane, so they're supposed to be flat, okay, perpendicular to the B's. Okay, so my geometry here is called a trigonal bipyramidal, which means that there are two pyramids that are trigonal pyramids that are stacked on top of one another. Okay, so what you have is this in the equatorial plane, and then leading up to the B, that's one pyramid, and that is stacked on top of another pyramid. Okay, so that's where we get the geometry. Now in this case, there are no lone pairs, so the electronic and molecular geometry match each other. Now just to note, you don't need to draw what I've drawn in green. I'm just trying to help you visualize the 3D picture. Now the angles here in this molecule, the angles in the equatorial plane are 120 degrees, because this is like a trigonal planar geometry with one atom coming up from the trigonal plane and the other atom coming down from it. And so the angle between the axial and the equatorial plane is 90 degrees. In our next class, AB4E, we have 4 atoms attached to the central atom and 1 lone pair. So again, we have a geometry of the electrons, or an electronic geometry, that is going to be trigonal bipyramidal, because we have a total of 5 electron pair domains around the central atom. Now, for this particular molecule, our decision of where the lone pair goes, whether it goes in the equatorial or the axial plane, depends on where there is more space. There is more space for the electron pair domain in the equatorial plane because the angle between those electron pair domains is 120 degrees. So the way that I draw this, I know my basic trigonal planar geometry. And I replace this bonded pair with my lone pair. Now, the shape of this is a seesaw. In order to be able to see that, you need to flip this on its side. So the wedge and the dashed line are like the fulcrum of the seesaw. You would have a person sitting here and a person sitting here. Okay, so that's why the geometry is called a seesaw. So sometimes we refer to this as being a distorted pyramid, okay, because these angles are all going to be distorted. In our next class, we have AB3E2. So in this case, we have 3 atoms attached, and we've got 2 lone pairs. Now, in this geometry, the electron pairs, again, are going to be in the equatorial plane. So our electronic geometry is trigonal bipyramidal, and the electrons pairs themselves will repel one another, so they will want the greatest distance between each other, which is best in the equatorial plane, because the lone pairs themselves will be at an angle of 120 degrees. I put the lone pairs where the wedge and dashed line were. You just put them on a little bit of an angle to show where they would be. Okay, and I do that so that I can see quite clearly the T shape of the molecule that results. If we've got 3 lone pairs and 2 atoms, again, the electronic geometry with these 4 electron pair domains in our expanded octet is going to be trigonal bipyramidal. The lone pairs need as much space as possible, so they will all be in the equatorial plane. And what we are left with is a linear molecule. I draw the lone pairs just on a bit of an angle. You don't need to try to put them on a wedge or anything, like I know in this diagram they do, but it's acceptable to just put them on a bit of an angle. So the resulting molecular geometry is linear. Moving on to our last type of electronic geometry, it's one where we have a total of 6 electron pair domains around the central atom. So in this case, all of what we have attached are going to be atoms. So we've got 6 bonding electron pair domains and 0 lone pairs. The best arrangement for these is in an octahedral geometry. So what we want is for all the angles to be 90 degrees. So essentially in the equatorial plane, if you think about it that way, we're going to have a square, and then above and below that, we're going to have another bond. So the angles everywhere in this molecule are 90 degrees. So I'll show you again with another color, okay, how this is an octahedron. So this is in the equatorial plane. Okay, and we have an octahedron. What an octahedron is an 8-sided shape. So it's kind of like a square-based bipyramid, but the entire thing is an octahedron, which is an 8-sided shape. Again, there are no lone pairs, so the electronic and molecular geometry are identical. And the angles are all 90 degrees. In our next class, we'll add 1 lone pair. So we've got 5 atoms attached and 1 lone pair. So the electronic geometry is going to be octahedral in this case because there is a total of 6 electron pair domains. Where we choose to put the lone pair does not matter because we are dealing with a geometry where all the angles are 90 degrees. So really, any spot is fine. I choose to put my lone pair on the bottom so that I can see the square-based pyramid that results. Okay, so this is my square-based pyramid. And it just helps you, again, if you can visualize the shapes, it's much easier to remember their names. And we've arrived at our final geometry, and that's one where we've got 4 atoms attached. And we've got 2 lone pairs. So again, we've got an electronic geometry that's octahedral because we have a total of 6 electron pair domains. In this case, we need to decide where the electrons are going to go, and the key is for the electrons to be as far away from one another as possible. So if we keep with our example from before, we had put the lone pair on the bottom, so the best place is exactly opposite. The reality is we could put it here and there, or here and there, but again, I like to keep them in these spots to be systematic and to be able to see the geometry here. It's square planar. My dash line, it's difficult to draw with this pen. All right, so what we have here is a summary, and this is table 10.2 in your textbook, and it shows a really nice summary of all the molecules that we've seen with lone pairs in them. And that concludes our lesson of the VSEPR Theory.